Okay, before I hit the Nernst equation, I want to spend some more time in calculating the standard potentials of electrochemical cells from the regular standard electrode potentials for the half reactions that would be provided to you in a table, just like I provide you the periodic table, but you should know how to use that. So the question I am interested in solving is that you have been given an equation. The equation looks like aluminum solid is reacted with nitrate, NO3 negative, which is in aqueous phase, and this is all in acidic media, so that will be a proton in aqueous. That gives you Al3 plus. We have NO, that's gaseous, and we have water. And so hopefully you can see that this particular reaction is a balanced reaction, because you have 4 positives on the left side, 1 negative, so a total of plus 3 charge on the left hand side, plus 3 charge on the right hand side, 1 aluminum, 1 nitrogen, 4 protons, so 2 times 2, and 3 oxygens on each side. So this is a balanced reaction. If I were you, what I would do is I would identify still, for the sake of argument, seeing what's oxidation, what's reduction, and that helps in determining the E0 cell. So oxidation here is aluminum to Al3 plus. Hopefully you can see that that's the loss of electrons. The 3 electrons are being lost, and reduction is going to involve the nitrate, NO3 negative, reacting with the 4 protons, accepting those 3 electrons, giving you NO plus 2H2O. And so when you add the two together, basically the 3 electrons will cancel off, and what remains is your overall reaction. So as we discussed earlier in one of the screencasts, that oxidation is what takes place at anode, reduction is what takes place at cathode. If you have to determine the E0 cell, what you will do is you will determine the cathodic reaction, and you'll determine the E0 from the table, and you will subtract the anode from the cathode and get your value. So let's read the table. Now the reduction potential value for anode is, so that means Al3 plus to aluminum, that is given to be negative 1.66, and the cathode for the reaction that we have nitrate plus 4 electron plus 4 protons and 3 electrons, that is given to be 0.96. So I write 0.96 minus 1.66, and that comes out to be 2.62 volts. Notice the E0 cell value that you obtain is a positive value, and since it's a positive value, you can perhaps envision that this reaction should be spontaneous, because when it's time to determine the delta G, which is negative NFE0, for the cell, since E0 will be a positive value, the overall value will be negative, and you would be able to predict that this particular cell should work on its own. So in the dry lab, I believe there are like 4 questions that are based on this idea, and in all of these you have to do the same thing: identify what's oxidation, what's reduction, and that will give you the idea as to what's oxidation, what's reduction. Get the anode, get the cathode, and just go cathode minus anode for the reduction potential values. You don't have to change the sign, you have to use them as is. And if your E0 cell happens to be a positive value, of course your delta G will happen to be a negative value, which will mean a spontaneous reaction. Now, a lot of times you might have to even predict the direction as to what's the anode, what's the cathode. So I just want to take an example and explain the same thing, reiterating a couple of things. Realize that whenever we have a half reaction and it has a negative electrode potential, that basically would mean that that particular electrode will have a tendency to lose electrons and therefore undergo oxidation, because the negative charge is going to repel the electrons, and the half reaction having more positive electrode potential will tend to gain these electrons and thus undergo the reduction, because positive charge is going to attract the electrons. So if you have two reduction half reactions, and I'm going to write both of these down. Let's say I have nickel 2 plus, which is reacting with 2 electrons to give you nickel solid, and E0 is going to be equal to negative 0.23 volts, and then we have Mn2 plus 2 electrons, which gives you manganese solid, and E0 here is going to be negative 1.18 volts. Hopefully you can see that in between these two reactions, the manganese half reaction has a more negative electrode potential. What does that mean? That means that it repels the electrons and proceeds in a manner which is reflective of an oxidation reaction. That means that manganese will actually lose electrons to give you Mn2 plus plus 2 electrons. That's what it means. And so more negative is the reduction potential. That means that that particular uh, uh, electrode is going to go through oxidation. So in this case, we're saying manganese goes through oxidation. And since the nickel half reaction has a more positive or less negative electrode potential, this is the one that attracts the electrons and proceeds in the forward direction. Realize it is a 2 electron change. So basically, if you add the two electrons is going to cancel off, and your overall reaction is going to look like nickel 2 plus manganese gives you nickel plus Mn2 plus aqueous. And so if you had to determine the E0 cell, the overall value can be determined by looking at E0 cathode. From that we will subtract out E0 anode. And so the cathode in this case is going to turn out to be negative 0.23 volts, because that is my reduction reaction. And from that we are going to subtract out negative 1.18. So sounds like our overall value will be a positive number. On my calculator, it's showing me 0.95 volts. So the overall cell potential is a positive value. This is indicative of a spontaneous reaction. And if you were to, give the cell representation, you would say that at anode, manganese is going to become Mn2 plus, aqueous, salt bridge, nickel 2 plus is going to become nickel, aqueous to solid. And that's going to be your cell representation. Now, one might envision another way of predicting the spontaneity of the reaction. Since our reactivity table that basically lists half reactions in order of decreasing electrode potential, so basically it provides more positive numbers on top and more negative values at the bottom. Anytime again we are saying that we have a positive electrode potential, that means the tendency to because it has a positive electrode potential, it will have a tendency to attract electrons and hence undergo a reduction reaction. On the other hand, more negative values will mean that they are going to repel electrons and therefore tend to occur in a reverse direction. So in other words, oxidation reaction is going to take place. So you can perhaps envision that if you have, some elements or some entities that have positive electrode potential and they are undergoing reduction, and at the anode you have a entity which lies lower than these four perhaps, and it has a negative value. You can envision that reaction will be spontaneous because the species which has a greater tendency to go through the oxidation reaction, it does have that negative value, and so when you go to calculate E cathode minus E anode, the overall value will end up being a positive number. So hopefully you can see that, again, to summarize, positive electrode potentials attract electrons strongly and hence will undergo reduction because it's a gain of electron. These will also be good oxidizing agents. So right side of the periodic table is where you will find most of these. Half reaction with more negative electrode potentials, they are going to tend to repel electrons better, and these will be good reducing agents. And of course, when you're thinking about the spontaneity of the reaction, you need to calculate the E0 cell and hence predict the delta G. That's the safest way to go about this, but you should be able to predict. And if it happens that you end up getting a non-spontaneous reaction, all you got to do is reverse the polarity. So what you thought was anode is going to be the cathode and vice versa, and you should be able to get your spontaneous cell that way. Let's see if we can use that to predict the spontaneity of a redox reaction. The question given here is that you have been given an equation, and you have to look up the table and see if this reaction, the way it's written, is going to be spontaneous or not. So hopefully you can see that here I have iron, which is becoming iron 2 plus. So we are trying to suggest that iron is going through an oxidation reaction with the loss of 2 electrons, and magnesium 2 plus is going to gain electrons, giving you solid magnesium. Now, if you look up the table will show you that magnesium, the reduction potential of magnesium, so Mg2 plus 2Mg, that number is a minus 2.37 volts. And when you look at the number for iron, that value, Fe2 plus 2Fe, that value is negative 0.45 volts. The rule is that greater is or more negative is the value that should mean oxidation. But from my reaction, I had predicted that iron should be the one that is going through the oxidation process. So probably the way this reaction is written, it's actually a mismatch. It's not possible, so the reaction will not be spontaneous. You will actually have to change the polarity. So what that means is that you will basically put in magnesium in Fe2 plus, and that will give you Fe and Mg2 plus, and that will be a spontaneous reaction. So you'll have to change the polarity. The product becomes the reactant. Based on this idea, hopefully you can see that you can also be you would also be able to predict whether a certain metal will dissolve in an acid. Of course, a lot of metals do, but then only those metals, you can envision, only those metals will allow the reduction of H plus ions into hydrogen gas, which are more reactive than it. What I mean by that is that if you consider something like, let's say, zinc. So you consider zinc can undergo Zn2 plus, 2 electrons will be given, and H plus from the acid can gain those electrons and give you H2 gas. Solid, aqueous. So now when you add the two, of course, the two electrons cancel off, and this can take the format of a single replacement reaction that you probably can envision from General Chemistry 1. Gas, aqueous, aqueous. So only if you see metals which are higher in reactivity would you see that this dissolution will take place. Again, this can be explained on the basis of E0 cell. So if you notice, for the case of zinc, this value is negative 0.76. Let's write that separately first. So E0 zinc. Zinc is negative 0.76, and H plus, of course, is 0. And so when you have to determine the E0 cell, you go cathode minus anode, and that gives out a positive value, and that would mean that the delta G is going to be negative, and you would be able to see the reaction occur spontaneously. So hopefully you have been able to understand, realize from the reaction, or rather the equation that we have been discussing, delta G0 is equal to minus NF E0 cell. And so if the E0 cell happens to be a positive value, the delta G0 automatically will be a negative value, and you're going to say that it's a spontaneous process. Another thing that we learned in thermodynamics was that delta G0 is equal to negative RT ln K, which was a good way to kind of tie in the equilibrium constant. So if you consider these two equations sort of simultaneously, hopefully you can see that since the left hand side is the same, then the right hand side should be equal as well. And so one can say that negative NF E0 cell is equal to negative RT ln K. Negative and negative can cancel out, and you can say that E0 cell is equal to RT over NF natural log of K. And if you simplify this for temperatures to be 25 degrees Celsius or 298 Kelvin, and for Faraday it's a constant 96500 coulombs. R is a gas constant, has a specific value of 8.314 joules per mole per Kelvin. And so if you plug in all of this data together and you convert sort of the natural log into log of K, so plugging in, putting things in perspective, that would mean that you will need to multiply it by 2.303 as well. Your E0 cell value will come out to be 0.0592 divided by n for the number of electron change times log of K. That gives us a direct relationship between the equilibrium constant and the E0, and we can use that to figure out whether the forward reaction or the backward reaction is going to proceed. So if we are somehow able to calculate E0 cell, if we have a definition about or given information about the E0 for the electrodes, we should be able to determine that pretty quickly, pretty easily, and determine the value of K. And so we would be able to comment on how the equilibrium is going to proceed. Let's maybe run a proof of this. The question is that we have to calculate K, the equilibrium constant, for oxidation of copper by H plus. So what I'm trying to say here is that copper, when you put it in an acid, and Cu2 plus an H2 gas is generated. That's our kind of tentative equation, the concept that we are going to address. and we are going to see whether or not this is a good equation. But just to kind of get you started, copper to copper 2 plus, that's an oxidation, so that must accompany loss of electron. Two protons are going to gain those electrons and give you the H2 gas. And of course, when we add, the two electrons are going to cancel off, and what remains, that is Cu solid plus 2H plus aqueous, is going to give you Cu2 plus aqueous plus H2, and that's your gas, the H2. And if you had to determine, the E0 cell for this process, you would say I'm looking for the E0 cathode minus E0 anode. And the numbers that you will use will be straight for the reduction potential values, because that's the convention. Again, E0 cathode, that's the hydrogen, so that's 0. From that, I'm going to subtract 0.34 volts, which is the value for copper. And notice my value came out to be negative 0.34 volts. That means the way this cell has been set up, if E0 itself is going to be negative, that should tell you that the reaction is going to be non-spontaneous, or in other words, is going to be a difficult reaction to begin with, a slow reaction to begin with. But we still need to prove our point, so let's see if we can determine the E0 cell, and that is 0.0592. Divide that by n, the number of electrons, which by the way is 2 electrons in this case, log of k. And so if you had to determine log of k, you would say negative 0.34 times 2 divided by 0.0592 is equal to log k. And so one can safely say that log k, I'm going to kind of shift, I want to still stay on the slide, log k is going to be equal to negative 11.48, or that k is going to be equal to 3.3 times, just a second, looks like minus 12. That's a pretty small value, and that should tell you that since it is such a small value, the backward reaction is going to be more predominant, and the equilibrium is not going to go in a forward direction. Now, another thing that is kind of striking in all of these problems are that more than often you would see that we use like a 1 molar solution, or we will use E0 cell. So that naught essentially basically gives you that if the concentrations are being referred to, we are going to take 1 molar. If temperature, we are going to consider 298 Kelvin. If it's pressure, we are going to consider 1 atmospheric pressure. But does that mean that reactions don't occur at temperatures or pressures or concentrations other than these standard conditions, or do we have to basically figure out a different way? And the answer to that is the latter. You need to think about what the equation, what the reaction would be like in a non-standard state condition, and it's going to basically employ something that you have seen in the past. Recall from chapter 18 that delta G under non-standard state is equal to delta G0 plus RT ln Q. And from here, actually, we get that equation that delta G is equal to negative RT ln K, because Q tends to K, and at that time the delta G tends to 0. So we had used that relationship. And if we plug in numbers, if we try to calculate values based off of that, we can see negative NF E cell, because this is delta G, so the 0 is gone, is going to be equal to negative NF E0 cell plus RT ln Q. And so in this case, you can perhaps see, you can envision that since you have R and T, which are constants, you can perhaps divide both sides of the equation. Divide by negative NF, and that gives you E cell is equal to E naught cell minus RT over NF natural log of Q. And if you plug in again for temperature of 298 Kelvin, R of 8.314 joules per mole per Kelvin, F is Faraday, that's 96500 coulombs per mole. If you plug these values in, you would be able to say that E cell is going to be equal to E naught cell minus 0.0592 divided by N log of Q. And that is Nernst equation. So Nernst equation basically provides you a relationship where E cell for the reaction or the half reaction can be calculated under non-standard state conditions when one or maybe all of the components are not present in their standard state, but you would still be able to determine the value of E cell. You call that equation Nernst equation. Alright, let's try to apply the concept of Nernst equation on a problem. The question here is, determine the cell potential of an electrochemical cell based on the information that is given. You're given that there's an oxidation reaction. That means the nickel reaction will take place at the anode. And then there's a reduction reaction. That means the vanadium oxide reaction will occur. That will take place at the cathode. Notice the concentrations have been provided in parentheses. So you're given these half reactions for the overall redox reaction, and so you should first take the time to kind of consolidate the data. That's what I would do if I were you. So strategize, conceptualize what you have to do with this data. You know that if you can determine the E naught anode and E naught cathode, you should be able to determine the E cell. You know that because we know that E naught cell is nothing but cathode minus anode. So we can simply get that information directly from your table of electrode potentials, and those are the reduction potential values again. And of course, in Nernst equation, we know that E cell, which is what we want to determine, that is nothing but the right side is E naught cell minus 0.0592 divided by N, the number of electron change, and log of Q. So if we can determine, the value of Q, we should be in business. So let's first get the numbers from the table and go from there. So on my table, I'm looking at nickel, where are you? Nickel 2 plus 2 electrons giving nickel. That is at negative 0.23. So Ni, let's write that. So E0, Ni, 2 plus 2, Ni, that is given as 0.23 volts. So that's my oxidation reaction, written as reduction. So notice here I'm showing you 2 plus 2 nickel, which means gain of electron. But like I said, these are always written by convention as reduction potential values. We've discussed this in really good detail in previous videos. The cathode reaction, which is the vanadium reaction, So that is for VO2 plus, and that number would be a positive value. That's exactly at 1. So vanadium to vanadium oxide 2 plus, that value is 1.00 volts. Okay, this is a minus 2 point. Okay, so now we are just going to start consolidating what we know about the concentrations. Hopefully you can recall from equilibrium that Q is the reaction quotient. And so if I think about my overall reaction, I would be able to say that I'm supposed to multiply this vanadium reaction, I'm supposed to multiply that by 2. And the reason you need to do that is because you have a 2 electron change. And so since in the bottom reaction you see only 1 electron, and since electrons do not participate in your overall reaction, they are only part of the half reactions, they do get cancelled in the balanced reaction, you should multiply the bottom reaction by 2. So your overall reaction is going to look like nickel solid plus 2 vanadium oxide, so VO2, plus 4 protons gives you nickel 2 plus 2 VO2 plus 2 H2O. And the 2 electrons are going to cancel out, which is why I'm not writing that. So if you had to write down the Q for the reaction quotient, you're going to just follow the law of mass action. Everything which is aqueous is going to count. Anything which is liquid is not going to count. So all charges, of course, are going to count. Anything which is a solid is not going to count as well. So your Q is going to look like nickel 2 plus times VO2 plus square of that divided by VO2 square of that, and H plus raised to the power of 4. And now we are going to just basically put in the values. So we have a value of Q. So nickel is at 2. Vanadium is at 2 molar as well. We are going to take a square of that. We'll divide that by 0.01 square of that. And acid is at concentration of 1 raised to the power of 4. So looks like you have something that looks like 8 divided by 1 times 10 to the negative 4, or you could say it is 8 times 10 to the 4th is the value of Q. Now we are simply going to use the Nernst equation like I was talking about earlier. E cell, which is what I want to determine, is going to be equal to E naught cell minus 0.0592 divided by 2 electron is the electron change, log of Q. So that will look like E naught cell, like I was saying, is a combination of the cathode and anode. So cathode minus anode. So let me write that. Cathode is 1 minus 0.23. So that gives you E naught cell. From that, I'm going to subtract 0.0592 divided by 2 log of 8 times 10 to the power of 4. So you have something that looks like 1.23 minus 0.0592 over 2 and log of whatever. Let me just solve that on my calculator. And that whole thing, this whole thing, pans out to be 0.145. So inclusive of the log as well as the multiplication factor dividing by 2, all of that. So all we're doing is 1.23 minus 0.145, and that will give me my final answer, which looks like is 1.085. 1.085 volts. So it makes sense. E naught cell value was the maximum value when the cell would have been just started, and at specific concentrations now, when the cell has been used, the potential is lesser. That tells you that the E cell at any given point of time is a measure, essentially, that is dependent on the concentration of the reactants. And so if you envision, what's that ad on TV? The bunny, Energizer bunny, keeps going, keeps going, keeps going. Why does it keep going? Because in that case, the concentration of the reactants is significantly higher, and so the battery lives for a very long time. So hopefully you're able to correlate that idea here. Now, one thing which I would like to point out here is that when a redox reaction within a voltaic cell or a battery occurs under standard conditions, that means that Q is equal to 1. So I'm kind of taking you back to, the Nernst equation. So we said that E naught cell minus 0.0592 divided by n log of Q is equal to E cell. That's what we said. And now we are saying that that Q is equal to 1. Standard conditions, Q is equal to 1. That means the amount of reactant and the product is basically equal. In that case, you can hopefully envision that since it will be log of Q that you will have to deal with, which will turn out to be 0, that means this whole term is going to get cancelled. And in such an event, you can say that E cell will be equal to E naught cell. So if you have an equation in which you have your reactants and products in a manner that they're equal, the value of Q is 1, you're going to get the same E cell as E naught cell. On the other hand, when a redox reaction within a voltaic cell occurs in conditions such that Q is less than 1, so if Q is less than 1, that means the greater concentration of reactants relative to the products. That will drive the reaction to the right-hand side, and that tells you that the E cell in that case is going to be more than E naught cell, because log Q, this whole term essentially will turn out to be a negative number. So negative times negative will be a positive value. On the other hand, if you have a situation, so let's just write that down first. Q less than 1, that means log Q is negative, implies E cell is going to be greater than E naught cell. And then if Q is more than 1, in that event, essentially you have greater concentration of products than the reactants. So the backward reaction is going to be more predominant. That's what in terms of equilibrium, that's what you expect. And so E naught cell is going to be less than E cell is going to be less than E naught cell. But what happens at equilibrium? So at equilibrium, Q tends to become equal to K, the equilibrium constant. And in such an event, the redox reaction has essentially no tendency to occur in either direction, and the E cell in that case will turn out to be 0. So this last point explains why batteries do not actually last forever, because as the reaction kind of gets depleted, as the reactants get depleted, the reaction will proceed towards equilibrium and the potential will tend towards 0. So you can say that as Q tends to K, E cell tends to 0, and you will end up with a dead battery. All right. So hopefully you can see, in this case, just to just to kind of make sure everybody's on board. What I just wrote, if I plug that in on my Nernst equation, I said E cell is 0, E naught cell is negative 0.0592 divided by n log of k. Notice my use of k instead of q because q was tending to k anyways. So as the reaction quotient becomes equal to the equilibrium constant, one can say equilibrium will be achieved, and once it is achieved, we are talking about a dead battery. So if we rearrange that, this equation in red can be written to be equal to log k is equal to n E naught cell divided by 0.0592. So what I'm doing here is I'm going to add, just to make sure everybody understands the math, I'm going to add the entire term 0.0592 divided by n log of k. I'm going to add that to both sides of the equation. So my equation will start looking like 0.0592 divided by n log of k is equal to E naught cell. And now I'm going to say that I'm going to multiply by n, multiply both sides by n, and divide by 0.0592. So when you do that, log k would remain on the left hand side, and the right hand side will start looking like n E naught cell divided by 0.0592, and that'll be your equation. So if you can determine E naught cell, if you know the number of electrons, you can perhaps determine the equilibrium constant, and hence you would be able to say whether the reaction is going to go in a forward direction, backward direction, or what. On the other hand, you can also use the equilibrium constant and the number of electrons to determine the E naught cell, so one way or the other. Let's see if we can apply this on this one question. The question is calculate K from the cell potential for reaction below. So we just saw a version of Nernst equation, which is log K is N E naught cell divided by 0.0592. So if I know the number of electrons, this is the number of electrons. If I know E naught cell, which I can simply get from the table, I should be able to determine this. So notice Pb2 plus is becoming Pb, Fe is becoming Fe2 plus. So it looks like my equations are Fe2, Fe2 plus 2 electrons, and Pb is gaining the 2 electrons. So the 2 and 2 will cancel off, and when you add the 2, they're going to give you the equation that we are talking about. So that means the value of n here is 2. Let's talk about the E naught cell. So in my table, I'm looking at Fe2, Fe2 plus, and my electrode potential E0 for Fe2 plus to Fe, that reduction potential is given to be minus 0.45 volts, and for lead, that value is given to be Pb2 plus to Pb. That value is given to be negative 0.13 volts. And that makes sense because the lead, which is expected to go through reduction, has a less negative value, so we can use that. And now we are going to plug in our numbers. So in my formula, log K is going to look like 2 times cathode, which is the lead, because that's where reduction is taking place. Anode is where the oxidation is taking place. So I'm going to say minus 0.13 minus 0.45 divided by 0.0592. And I'm going to punch in, I'm going to try to calculate these values. So the right hand side begins to look like, let's see, 2 times 0.32 divided by 0.0592, and that value comes out to be 10.8108, and that's my log of K. So now if I have to take my anti-log, I have to go shift or second, and so K turns out to be 6.46 times 10 to the power of 10. That's a pretty gigantic number. And it makes sense because my electrode potential came out to be a positive value. It came out to be 0.32 volts. So that was a positive value that indicates it's a spontaneous reaction. That indicates that the equilibrium should lie on the right hand side towards the products, and that's what we saw. So K is equal to 6.46 times 10 to the power of 10. Of course, K doesn't have the units, and that is going to be your final answer. Okay, let's finish Nernst equation through concentration cells. Now, hopefully, through the Nernst equation, you can envision that E cell depends on E naught cell, and also depends on 592. Also depends on the reaction quotient, which is kind of like a concentration gradient. So it's not just the cell potential, but rather the concentration of the reactants and the products in those half reactions, which dictate, how the cell is going to work and what kind of difference in concentration would be, and how it would drive the current flow. So, for example, if you consider a cell in which, let's say, copper is oxidized at anode and copper ions are reduced at the cathode, so it's a copper-copper reaction. You have a Cu plus Cu2 plus. So Cu2 plus is going to gain the electron, become copper, and copper is going to lose the electron and become copper 2 plus. The Cu2 plus concentration is perhaps 2 molar, so that's a high concentration, and Cu2 plus is going to be at a lower concentration. So in this case, hopefully you can envision that this E naught cell is going to be equal to 0 because the anode and the cathode are the same thing. So you're subtracting, the same electrode potential from itself, and so that value will come out to be 0. But there is still a difference in concentration of the two half cells, and so the cell potential must be calculated using the Nernst equation. And so if you follow that and you plug in your numbers, you can hopefully see that 0 minus 0.0592 divided by 2 is the electron change here. Log of copper 2 plus is your product, so that's 0.01 divided by 2 is your reactant, and when you solve that, it comes out to be 0.068 volts. It's kind of low, but still it does have a potential. What does this mean? This means that electrons will spontaneously flow from the half cell with the lower copper ion concentration to the half cell with the higher copper ion concentration. So you can imagine that the concentration cells, in the same way you think about any concentration gradient. If you mix a concentrated solution of copper 2 plus with a dilute solution of copper ions, flow from concentrated solution to the dilute one. Similarly, in a concentration cell, the transfer of electrons from the dilute half cell resulting in the formation of the Cu2 plus ions in the dilute half cell. And so the electrons flow to the concentrated cell, which is where the reduction takes place, and you're going to see more and more Cu2 plus along the way. So the flow of electron has the effect in increasing the concentration of Cu2 plus in the dilute cell and decreasing the concentration of Cu2 plus in the concentrated half cell. Exactly what you would have expected in what is called as the concentration gradient. Now, of course, this concept can be, extended to the concentration cells in human nerve cells, for example. So you might have read, you might have studied in biology that there are tiny pumps of pumps that are present in membranes of human nerve cells, which basically pump sodium and potassium ions through those membranes, and establish sort of like a concentration gradient for each ion. And so the concentration of the sodium ion, so if you have this membrane, the concentration of sodium ions is higher on the outside than it is within. And the exactly opposite is true for potassium. So you have more potassium inside, you have less sodium inside, you have more sodium outside, less potassium outside. And so these concentration gradients basically have what is called as like a resting potential. So, when we don't have a nerve impulse. So that resting potential is usually a pretty low value. The interior of the cell is negative 70 millivolts. Negative 70 millivolts. And when the cell is stimulated, what happens is that some channels within the membrane, let's maybe show the channels with a different, some channels, they essentially open. So when they open, what happens is that they allow the sodium to rush into the cell. And as that happens, it changes the potential to temporarily rise, and the value changes from negative 70 to about positive 30 millivolts. And so this is basically followed by, this is a concentration gradient which has changed, because of which the E cell has changed as well. And so this is followed by opening of other channels through which the potassium is going to gush out. So potassium is going to leave. And so it will bring the potential back to near the resting potential. And this result, basically it results in spike of a change in electrochemical potential across the membrane, which provides the stimulus to the neighboring segment of the membrane. And in this way, the electrical signal moves through down the length of the nerve cell and into the next neighboring nerve cell. So when the electrical signal essentially reaches the end of your nerve cell, and then the axon and whatnot, so when it reaches at the end, that's when the chemical neurotransmitter that gets released, and that travels to the next cell, and essentially the same kind of electrochemical spike is seen. So the neural signal travels through the brain and the nervous system of the human being through a concentration gradient and an electrochemical change in the potential. Just so you know.